Modern large language models write code, pass medical exams, and reason through complex logic. Yet to the engineers who train them, they operate as uninterpretable black boxes. The training sets billions of parameters, but the internal logic remains hidden. The field of mechanistic interpretability exists to solve this exact problem. The goal is to reverse engineer these learned alien neural algorithms and translate them into human-readable computational graphs. Anthropic approached this massive engineering challenge from the bottom up. To map the architecture of frontier models in 2024, researchers recognized they first had to establish mathematical proofs on highly simplified toy models in 2021. The 2021 starting point involved building 1- and 2-layer attention-only transformers. Researchers intentionally stripped away complex components like layer norms and MLPs, the feed-forward networks that process data after the attention mechanism. Removing them allowed researchers to observe a clean flow of data. Decoding a trillion-parameter system requires foundational ground truth. By isolating the absolute smallest computational units of a neural network, researchers could prove whether these systems could be mathematically decoded at all. In these stripped-down, attention-only models, computation is driven by two primary circuits: the query key, or QK circuit, and the output value, or OV circuit. The QK circuit is the routing system. By calculating the relationship between a query and key token, it determines where information moves. Then, the OV circuit acts as the payload, dictating what specific information is extracted and moved along that path to the destination. By analyzing these two circuits together, researchers achieved something rare in deep learning. They perfectly contextualized every single parameter in a one-layer model. This direct matrix reading approach represented the gold standard of pure mathematical interpretability. It required no guesswork, only linear algebra, but it carried a fatal limitation. This manual reading process only works when the multi-layer perceptrons are absent. As soon as researchers added MLPs back into the architecture and scaled the models up, direct matrix reading broke down entirely. The math became hopelessly entangled, forcing the field to confront a roadblock in deep learning. For years, the machine learning community relied on an assumption called the neuron doctrine. This hypothesis posited that one artificial neuron maps cleanly to one distinct human-readable concept, like a specific neuron activating only for the color red, or the concept of a dog. Anthropic's analysis of scaled networks proved the neuron doctrine false. When looking inside the MLP layers of larger transformers, researchers found that individual neurons fire unpredictably for completely unrelated features. In one specific case study, researchers isolated a single neuron and observed its activation patterns. It responded simultaneously to academic citations, English dialogue, HTTP requests, and Korean text. This phenomenon is known as Polysematicity. Because a single neuron responds to a chaotic mixture of different inputs, analyzing individual neurons in the MLP layer is functionally useless for understanding the model's reasoning. If single neurons do not correspond to distinct concepts, the true fundamental unit of computation must be hidden elsewhere within the network's architecture. The underlying mathematical cause of polysemanticity is a mechanism called superposition. Look at this baseline 3D vector space. A network can represent a concept clearly and distinctly if that concept aligns perfectly with a single-dimensional axis. Here, 3 dimensions easily hold 3 separate concepts without interference. But neural networks are forced to maximize efficiency. To process vast amounts of data, the network crams far more concepts into its architecture than it has actual dimensions. It encodes these extra concepts as linear combinations spread across multiple neurons simultaneously. This extreme data compression causes mathematical interference. It turns the MLP layer into a dense, uninterpretable knot of overlapping activations, where no concept can be isolated by looking at a single node. Superposition proves that the true features of a language model are not the individual neurons. The true features are hidden, multi-dimensional directions buried within the activation space. In 2023, Anthropic published Towards Monosemanticity, detailing a mechanical solution to untangle this superposition knot. The extraction tool they utilized is called dictionary learning, executed via a sparse autoencoder, or SAE. An SAE is a secondary neural network trained specifically to find the hidden, uncompressed structures inside the primary language model. This animation shows the first step of the SAE process. It takes the dense, superposed activations from the transformer and forces a dimensional expansion, blowing the data out into a significantly wider, high-dimensional hidden layer. The second crucial step applies an L1 sparsity penalty. This mathematical constraint forces the vast majority of these newly expanded nodes to turn off. The network is restricted so that only a tiny fraction of nodes can be active at any time. By forcing dimensional expansion and strict sparsity, the SAE mathematically unravels the compression. It creates an overcomplete basis, a wide, sparse landscape where individual features can finally be read. The ultimate output of the sparse autoencoder is the successful recovery of monosemantic features. Unlike the chaotic neurons in the standard model, these monosemantic features are discrete vectors that fire strictly for highly specific contexts. These features eliminate the confusion of polysemanticity. When applied to a one-layer transformer in 2023, the SAE successfully extracted foundational concepts. Researchers isolated distinct features that acted as strict detectors for DNA sequences, for Arabic script, and base64 strings. To validate that these features were accurate, researchers used a separate large language model to generate automated explanations for the activation patterns. The tests proved the features consistently fired for their assigned concepts without bleeding into unrelated topics. The SAE effectively acts as a translation engine. It successfully converts the alien, compressed logic of the machine back into isolated, readable human concepts. In May 2024, Anthropic reached a major milestone with the publication of Scaling Monosalmon-City. They scaled the SAE technique by orders of magnitude to analyze a live, production-grade model. The sheer computational scale of this achievement was massive. The team successfully extracted millions of distinct features from the middle layer of Claude 3.0 Sonnet. The 2024 features moved far beyond simple token detection. Researchers found deep conceptual abstractions, including the discovery of an active inner conflict feature. This scatterplot maps the contextual environment of the inner conflict feature. Notice how it logically clusters near related abstract concepts, including relationship breakups, logical inconsistencies, and catch-22s. This topological map proves that the internal organization of a language model's concepts genuinely corresponds to human notions of similarity, reasoning, and metaphor. Mapping these features carries immediate safety implications. It provides the exact coordinates needed to locate features associated with misuse, bias, and manipulation. Within Sonnet, researchers identified a specific sycophantic praise feature. This feature activates heavily when the model encounters user compliments or flattery. Finding the feature enables steering or clamping. This is the process of artificially forcing a specific feature to a high activation value during a live forward pass, essentially dialing it up to maximum regardless of the input. The behavioral result of this intervention is immediate. When the sycophancy feature is clamped, the model's output alters, providing fawning, untruthful responses to an overconfident user. Identifying and manipulating these features provides a direct mechanistic lever. It lets researchers control AI behavior and monitor cognition before harmful text is ever generated. Despite the triumph of extracting millions of features, the field of mechanistic interpretability is still confronting massive open problems. The next critical bottleneck is functional routing. Isolating a feature tells us what the model knows, but it doesn't explain how the model uses it. Researchers must now trace the multi-layer circuits these features form across the entire network. The near-term engineering goals of the field involve using these mapped features and circuits for automated auditing, enabling real-time monitoring of unsafe cognition during active deployment. The theoretical end state of the discipline is formal verification. This is a standard where safety properties can be mathematically proven for any input, treating AI with the same rigorous guarantees as mission-critical software. Anthropic's 4-year trajectory, from parsing toy matrices to mapping Claude's inner abstractions, indicates that the internal logic of these systems is mathematically accessible. We are developing the lens required to read it.